This was bar none the biggest thing humans ever built. 459 meters long, longer than a skyscraper, is tall, and heavier than a small island. That size defined everything that followed. How it was built, how it sailed, and how it also didn't really work. This was the Seawise Giant, the world's largest man-made vehicle. The concept of the Giant was simple in commercial terms. Scale-up tanker design to achieve very long, high-volume crude oil runs. It was built by Sumitomo in Yokosuka and began as Hull 1016 in the factory, where it was later made massive to reach the dimensions it became famous for. The basic propulsion and mechanical layout were old-school heavy engineering, steam boilers and turbines rather than modern diesel giants. This was combined with an AP steam turbine supplied by Mitsubishi-built boilers and produced roughly 50,000 horsepower. This was a lot, but it was only enough to push the hull at about 16 to 16.5 knots in good weather. This was because when fully loaded, the ship could weigh in at around 657,000 tons. But this wasn't meant to go fast. When a vessel displaces hundreds of thousands of tons, speed isn't the point. What really matters here is economy per barrel, or basically how cheap it was to move one barrel. And in this sense, it did a pretty good job. But oh boy, the drawbacks. Let's first take the situation at the time into account. In the late 1970s, the economics suggested that if you could move more oil per voyage, you could reduce per barrel transport costs despite inefficiencies elsewhere. The ship's hull was lengthened and refitted to increase cargo capacity, a controversial decision that added 146,152 tons of capacity during conversion. So, on paper, the ship was designed for hauling the maximum amount possible of crude oil in a single hull between deepwater terminals. They optimized per barrel cost by leveraging scale and operated where infrastructure could absorb that scale, unfortunately at the detriment to literally everything else. The ship's turning circle and stopping distance were enormous. It took roughly 2 miles to turn and 5.5 miles to come at a stop from that 16.5 knot speed. Maneuvering it required tugs, space, and planning. You couldn't just go where other ships went. It was also impractical by design limits. Her fully laden draft was 24.6 meters. This meant that there's 24.6 meters between the bottom of the hull and the waterline, which prevented transit through key choke points like the Suez Canal, the Panama Canal, and even many shallower ports. This meant operations had to be planned around offshore loading, transshipment, and routes that could accept the draft. Loading and unloading this beast took place at lightering operations or at very deep-water terminals. The ship had 46 cargo tanks and required enormous crews for maintenance and cargo management. The scale of its systems, fuel, ballast, inert gas, firefighting, and even piping, magnified ordinary tanker logistics by orders of a magnitude. Every spare part weighed tons. Every system required redundancy. Routine maintenance windows were long, dockings were complex, and insurance considerations were also extremely high. In structural terms, engineers had to account for hogging and sagging stresses along a hull approaching half a kilometer long. Longitudinal strength, tank spacing, and structural redundancy became the engineering focus. On top of all this, though, it was vulnerable to market shocks and geopolitical instability because the entire business model depended on predictable, high-volume oil demand and safe routes through one of the most politically fragile regions of the world. If oil prices dropped, the cost of operating such a massive ship suddenly wasn't worth it anymore. And if tensions rose where the ship usually goes in the Persian Gulf, which they often did, insurance costs soared, routes were disrupted, and tankers became military targets. A ship that large couldn't easily reroute or squeeze into alternative ports, so any shift in global markets or regional conflict hit much harder than smaller, more flexible vessels. It actually even sunk once during the Iran-Iraq War, but got salvaged and recommissioned. It came back later under many different names, including the Happy Giant, the Jar Viking, and finally the Knock Nevis, but that's a story for another time. Today, the Seawise Giant no longer sails. After a final oil sail and a voyage to Alang, it was beached for scrapping on the 22nd of December 2009 and was dismantled through 2010. The anchor was salvaged and donated to maritime museums. Pieces of that monumental engineering legacy now survive basically as artifacts. The hull itself is gone though, cut into sections and recycled. Despite all that, the record still remains, the longest self-propelled ship ever built. Another case study in where human ambition and industrial limits collide. In the end, the giant taught ship designers and policymakers about the limits of scale. Scale can reduce unit costs, but it can also concentrate risks. For a brief period though, a half-kilometer hunk of steel moved across the sea, carrying more oil than many nations consume in a month. And that spectacle still fascinates engineers, economists, and historians. So whether you view her as a triumph of engineering or as a cautionary tale of hubris, it still admittedly remains one of the single most extreme examples of humankind's ambition. And personally, I think that that's pretty neat. Thanks for watching. I'll see you guys in the next one. Peace.